Hi, everyone. Welcome to today's lecture. We are going to talk about sieve analysis today. So one of the first things that you do when you get your sample from the field, you are going to classify the soil. And by classification, we want to know what type of grain sizes and what type of material we have in the soil. Um, I'm going to share a screen with you. So as you have learned in your soil mechanics class, um, based on depends on the organization, we have different classification for soil. The one that we're using for this class is the Unified Soil Classification System, or USCS. Based on this classification system, for grain sizes between 4.75 millimeters and 76.2 millimeters, they're considered as gravel. Sand is the grain sizes between 4.75 and 0.075 millimeters. Gravel and sand are considered as coarse grains, and salt and clay, they are considered as fines, and they are smaller than 0.075 millimeter. So you need to know that 1 millimeter is almost this much. So it's very small. And then when you say 0.075 millimeter, it's really teeny tiny. So here, this picture might give you some idea that like in terms of millimeters or inches, how different the sizes of these grains are. So for gravel, you have this huge size, huge piece. For sand, is this one. Silt is like a dot, and clay, it's invisible at this scale. And when you have a soil, then you might have coarse grain soil, intermediate grain soil, or fine grain soils. So the first thing to do, based on what type of soil you're dealing with, you're going to choose the method for finding the grain sizes in your soil. In general, we have two methods. We have sieve analysis and we have a hydrometer analysis. And in this lecture, we are focusing on sieve analysis. And our first lab and our second lab is going to be hydrometer analysis. What the difference is between these two tests is that the sieve analysis are going to be used to find the grain size for the coarse grain, and hydrometer analysis is for the fines. And that's because they're too tiny to be able to identify using the sieves. So when we talk about sieve analysis, sieves, they look like this. They have different mesh sizes. As you can see, some of them are bigger, some of them tiny. The two important ones that we have to have is these two, which is 4.75 and 0.075, because if you have a sieve and your grain and your soil retains on this sieve, that means they're bigger than 4.75 millimeters and they're gravel. And if they pass through the 0.075 millimeters, that means they're smaller than 0.075 millimeters and they are silt or clay or fines. So 0.075 millimeter sieve and 4.75 sieve, they're the most important ones. One of them goes to the top and the other one goes to the bottom. Based on the type of soil you're dealing with, you may have other sieves on top of the 4.75, but for the purpose of this course, we start with 4.75, which separates the gravel from the sand. And these are like, this image shows how different the sizes are. As you can see, based on how big is the mesh, then the part or the grains that they retain on that sieve, they're different. So what we do in this lab, we put a set of sieves together, we stack them on top of each other. We put a pan underneath that 0.075 millimeters, and we put a lid on the top. And then we put this in the shaker and we shake it. As we shake the soil that is poured in the top sieve, if the grains are smaller than each of these sieve mesh sizes, they're going to pass through it, and some of the soil is going to retain on them. And after we are done, we take them apart and we measure how much soil is retained in each of these sieves. This picture shows the shaker. So you shake it for 5-10 minutes, and after that you take it apart. You measure how much soil is retained in each sieve. For that, you can pour. What you can do, you can put like a bowl on the scale and tear it to 0, and then you pour the soil into that bowl, and then see how many grams is that. And we usually start with 1 kilogram or 1,000 grams of the soil. It doesn't need to be accurate. It's just something about around that 1 kilo should be good. And one thing that you have to keep in mind is that the size of the sieves, the way that we stack them is from the large mesh to the fine mesh. So bigger grain's gonna stay on this one, the smaller one's gonna stay on this, and as we go, and the smallest one, which are fine, is gonna stay in the pan. We save the soil that stays in the pan, and we do hydrometry analysis on them, which we're going to cover in the second lab. And that's basically because they're too tiny that we can't use any sieves for them to see what are their sizes. They're really teeny tiny. So we don't throw out the soil that it's remain in the pan. So we need that soil. Okay, so I'm done with this file. I'm just going to close it. I just had some figures to show you guys, and now I'm going to open the handout that we have for the lab, and we go over the procedure to do this lab. Okay, I'm going to stop this share, and I'll share my lab handouts. So this is sieve analysis, and the goal of this is to classify the soil. This test by itself, it's not enough to classify the soil. We need the results from hydrometry analysis and also Atterberg limit test as well in order to classify our soil. So the first 3 labs that we are doing, the first one is sieve analysis, the second one is hydrometry analysis, and the last one is Atterberg limit. And then when we have all 3 tests, then we can classify our soil. These are the US sieve sizes. As you can see, I want you guys to memorize 2 of these, that the sieve number 4, that's the one that we use on the top, and that's 4.75 millimeters. And the sieve that we have on the bottom, it's going to be the 200, and that's 0.075 millimeters. Why it is important? Because number 4 is between gravel and sand, and number 200 is between gravel and sand and fines. So fines pass through the 0.075. So you have to memorize these 2. So if I tell you what is the biggest sieve number that we use and what's the smallest one based on the mesh sizes, you're going to say number 4 and number 200. And you have to know what is the size of the opening, simply because it's the size of the particle that we have. Okay, so the procedure is we're going to take 1 kilo of dry soil. Obviously, it should be dry. We don't need water. If you have a wet soil, you just air dry it, or you just put it in the oven and they dry out. Also, sometimes the soil just get stuck to each other and they create a lump, so you can break those, but you should not put too much pressure to break the particles. So it's just like you kind of like opening them up. And then we need to know how much soil we are beginning with. So you have to measure. It doesn't need to be 1,000, but it should be around that. You always have 2 ways to determine the mass of the soil. So sometimes you put the pan on the scale and measure how much the pan weighs, and then you pour your soil into it, and you find the mass of the pan and soil together, and then you subtract the mass of the pan from the pan and soil together, and you find the mass of the soil. Sometimes you can just tear it to 0. So if you put the pan and tear the scale to 0, then when you add the soil, you can tell, okay, how much soil you have. And then you pick your sieves and you stack them together. The way that we do, number 4 goes on the top. Then we're going to have number 10, 20, 40, 60, 140, and 200. If you have more sieves, that means you have more sizes of the grains in between the number 4 and number 200. So when you graph your so like a grain size distribution curve, it looks better because you have more points to create that line. In the lab, sometimes we don't have all these sieve numbers, so you have to just, instead of 40, you can use 30, or instead of like 100, you can use 100. That doesn't matter, but you need to have like enough numbers of sieves between 4 and 200 to make sure that the curve looks nice. We put them together. We put a lid on top so the soil doesn't pour out when we are shaking the stack of the sieves, and we put a pan underneath to number 200 just to collect the fines and keep it for the hydrometer analysis. And we put it in the shaker and we shake it. And after 10 minutes or 15 minutes, we take the sieves out, we separate them, and we pour the soil in each of the sieves into a bowl that we know how much it weighs. And then by subtraction of the total weight from the weight of the tray, we can find the weight of the remained soil or retained soil on each sieve. Now, the analysis that you're going to be doing for this test, you have to create a table like this in the Excel spreadsheet. You have the sieve numbers, and you can find the sieve openings in millimeters from this table that I just showed you. And then the mass retained on each sieve. So if we were doing this lab in the lab, we would measure this and we would put it in this. So what would you get from this lab would have been sieve numbers and the retained soil in each sieve. And the last three columns, you have to do the analysis to find those three. So if you look at the Excel spreadsheet that I have provided on Canvas for the data for this lab, sieve numbers and so column 1 and column 3 are given. You have to add the column 2, which is the sieve openings, and then you have to calculate these last 3 columns. And then you're going to plot the percent finer versus the sieve opening in millimeters. And that's going to be your grain size distribution curve. So how we can find these things? So you have the mass retained on each sieve. Then what we need, we want to find how much soil is smaller than that sieve. So we don't care about how much stayed on it. We technically care how much passed through it, because we want the percent finer than that sieve. So what we do to find this percent finer, we find the mass retained on each sieve, and then in percentage. So you have the mass on each sieve. How do you find the percentage? It's simply using this equation here. The mass retained divided by the total mass that you had at the beginning, which could be 1,000 or even less than that. Sometimes you lose some of your soil, they get stuck in the mesh. You need to make sure you should not lose more than 2% of your soil mass at the end. So if you do the summation of all these soil retained on your sieves, which is your sigma mn, this should be very close to the mass that you started with. You should not lose more than 2%. So for instance, if you had thousands grams of soil, you can't lose more than 20 grams. It should be less than that. So the mass retained on each sieve divided by the total mass times 100 gives you the percent of soil retained. And then what you do in the fourth column, you find the cumulative percent retained, which means, so whatever number you have here, then would be here. The number here would be the sum of these two, one here and one here, because this is cumulative retained. So you find that, and then to find percent finer, you simply say, okay, 100 minus whatever stayed on it, it would be the percent finer, and that would be your last graph. And you can find them here. So cumulative percent of soil retained would be sigma of our n's from 1 to n, and then passing through the n's would be just 100 minus whatever it's retained through it. And then you draw your graph. On the x-axis going to be the grain sizes in millimeters, and your y-axis is going to be the percent finer. The x-axis should be in millimeters, and it should be in logarithmic scale, but your horizontal or vertical axis is going to be the regular scale. There are a couple of things that you need to find. It's going to be D10, D30, and D60, which are the size of the grains, that 10% of the soil is smaller than that. D30 is that diameter that 30% of soil is finer than that. And 60 is going to be the diameter that 60% of particles are smaller than that. And why we need these things? We need this for soil classification, and we can find two factors from them, C sub U and C sub C. C sub U is D60 over D10, and we call it a uniformity coefficient, and C sub C is D30 squared divided by D60 times D10, and that is called coefficient of curvature, or coefficient of gradation. And I'm sure Dr. Oak has gone over these things in mechanics of soil mechanics. So here it says that your curve should be semi-log plot. X-axis is in log and y-axis is in natural scale. What it looks like, it's going to look like this. This is percent finer, and this is your grain sizes. As you can see, this is bigger than this, and you can in Excel reverse your numbers. So instead of starting from smaller to bigger, it starts from bigger to smaller. And that's the way that we usually show the grain size distribution. So not only you have to change this to a log scale, you also have to change the order of the values from bigger to smaller instead of smaller to bigger. So you have a graph like this. And then when you want to find this D10, D30, and D60, you look for this 60% finer, and then you find the diameter corresponding to that 60. And then for 30, same thing, you find the 30%, and then you find the diameter corresponding to that on the x-axis. Same thing for D10. And then you use these two equations to find C sub U and C sub C. Now what I'm going to do, I'm going to open the Excel spreadsheet file that I have. It's on Canvas, and I'll show you that how the data looks like. So I'm going to stop this. Just give me a second. Okay, so if you open the file that I have provided under the name sieve analysis underscore data, you'll see the mass of the dry specimen is 1,000 grams. The sieve numbers are given. The mass retained on each sieve is given. As you can see, if I here add these all together, this should be 1,000 grams, but it's slightly smaller. And that's because you lose some of your soil on the sieves. So it should be very small though, like under 2% of the entire mass of your soil, which is like 20 grams, and we're good. And so you are going to add one column here to add the size or diameter or grain or the mesh size. Just follow whatever it's on the table in the handouts in the manual, and I put in millimeters. And then, so for instance, for 4, you have 4.75, and for 200, you have 0.075. And then in between, you get it from the handout that you have. And when you are plotting your data, so you would go to insert, you enter, so you have to calculate percent finer eventually, percent finer in percentage, following the equations that we have. And then you would do insert graph, and your x-axis is going to be, so edit. The name would be grain size distribution. You just change it. I'm not going to change it. So for x-axis, we have the sizes. And for the y-axis, we have the percent finer, right? this graph is not going to look good simply because I don't have the data. Let's just put like something. Let's say here we have 80% passing through this and 40% passing through this, 49%. So edit X is going to be this, and Y is going to be this. So as you can see here, we don't have enough points. Obviously, you need more points, and then you have to change the plot type to, you change the chart type. You need the lines between them. So simply because we don't have all the points, it doesn't give us the curve. When you have all the points, it's going to give you the curve. So what you need to do for this one, first make sure to add the labels. So you need the, for each axis, you need to add the titles. Make sure that you have the units as well. And then what you do, you change the x-axis to, you just go to format axis and change that to logarithmic scale. And then you also, you put the, sorry, I lost my window. You go to format axis, and then here you put the values in reverse order. So now it goes from 10 to 0 instead of 0 to, and then you have the line here simply because this is logarithmic. 10 to the power of 0 is going to be 1. So this is your origin, is going to be here, 0 and 1. Okay, so you can change this axis title or move it to the left because that's nicer. And then also you can do add some borders around this. So make sure that the size of these are big enough, because when you put it in your report, it should look good. Okay, so that's about the analysis. I do have a video for sieve analysis that I want you guys to go and watch. That's from YouTube. That's something that I did. So that's why I didn't embed it in this video. So I don't get like a copyright error. Just the sieves that they're using in the test, it's a little bit different, or the sieve sizes that they're using. Just follow whatever it's here. So in the lab, we would use 4, 10, 20, 30, 40, 60, 140, and 200. Also for analysis, just follow your handout instead of the analysis in the video. It's not wrong. It's just to be consistent, just use whatever it's in the handout, the equations that we have. If you have any questions, please let me know, and I'll be happy to answer all the questions. Thank you, everyone. Bye.